Shall we?
Yeah. Okay, so hi everyone and everyone on Zoom. So it's a pleasure to have Antonis Antoniou and Lorenzo Lorenzetti today for our foundation webinar. So Antonis is a postdoctoral fellow in the Horizon project called Andromeda. On the philosophy of dark matter and modified gravity, and he's in the Department of History and Philosophy of Science at the National and Kapodistrian University of Athens. And Lorenzo is a postdoctoral researcher at the Institute of Philosophy and in Lugano, Switzerland. And I just learned recently that they were both actually supervised at Bristol by our colloquial speaker from last week, Corinne. Although I think, Lorenzo, you were also supervised by James Levy there as well. But anyway, today they're going to be talking to us about limiting reduction and modified gravity.
Okay, thank you all for being here, both physically and on Zoom. Apologize for not being able to be there with you, but fortunately this was not possible. Also, thank you to Helen for the invitation and the opportunity to talk at your seminar. So today I'm going to talk to you about limiting reduction and modified gravity. This is a co-authored work along with my colleague Lorenzo Lorenzetti. And basically, this talk is about how well modified Newtonian dynamics bears with existing accounts on limiting reduction. So I will start the presentation. I will present for the first part, and at some point I will hand over to Lorenzo, who will give you the second part of the talk. Now, what is modified Newtonian dynamics? For those of you who are not familiar with this theory, is a theory of modified gravity which was introduced in the 1980s as a possible alternative to the hypothesis of dark matter. So the central tenet of this theory is that standard Newtonian dynamics seeks to obtain below a critical acceleration constant, which we shall denote as alpha zero, where different laws of gravity apply, and this is the deep MOND regime. This is a deep MOND limit for very low accelerations. Newtonian gravity therefore becomes the limit of a broader classical theory of MOND, which in turn is the limit of a relativistic theory of MOND, which has to recover both the classical limits of modified Newtonian dynamics and the Newtonian dynamics in the appropriate regimes. Now, these kind of theories, they have a very special feature. They necessarily have to introduce an interpolating function to ensure that there is a smooth transition between the different regimes they have to accommodate. And this particular feature is basically what motivated us to start thinking about how this introduction of this interpolating function affects the transition between one regime to another, and how this relates to the broader framework of limiting reduction in the literature. So our main goals are to assess the validity of MOND theories through the lens of limiting reduction, and we will argue that it is not reduction-wise justified, at least in its current form. And this is actually a well-known fact. And we will also highlight how reduction can be helpful to assess the validity of physical theories, especially theories such as MOND that are not widely accepted and are proposals. Our analysis of this case study indicated the need to refine our understanding of limited reduction. So we will also make some suggestions on how we should understand limiting reduction in general. So the outline, I have just introduced you to our motivation. I will say a few words about limiting reduction in general. Then we will talk about modified Newtonian dynamics and the role of the interpolating function in these kind of theories. Then we will assess whether MOND theories are indeed valid cases of limiting reduction with a question mark. And then I will hand over to Lorenzo, who will make a parallel comparison with a well-known case of interpolation in the history of physics, the derivation of Planck's law for black body radiation. And then we will also compare MOND, how MOND compares to general relativity in recovering the Newtonian limit. And we will close with our discussion and some conclusions. So the starting point for the standard account of limited reduction we take to be Nichols' seminal paper on limited reduction. So the general idea is that if we have a quantity of a theory T1 and a quantity of a narrower theory T2, then this quantity reduces to the corresponding recovering theory by taking the upper limit or the lower limit. And Nichols says that the limiting operation should make physical sense. Now, what this means for Nichols, here is how he puts it. It is important that the reductive operations make physical sense. By taking the limit as temperature T goes to infinity, we may be able to eliminate T or a more complex factor involving T from some theory. So this is in the context of thermodynamics, of course. But an infinite temperature does not make physical sense, nor does it make physical sense to allow T to vary normally, but to eliminate it by introducing a special new multiplicative factor to which no physical interpretation can be assigned and on which the limits are taken. So for Nichols, what matters is that we don't have any unphysical factors or infinities which don't make physical sense, and that we should be able to give some physical interpretation to the limiting factors we introduce to recover the narrower theory. That's the idea. Now, this idea has been taken from Butterfield, who wanted to address the worry for the infinities and formulated what some people call Butterfield's principle. So Butterfield asks the question, when is a mathematical limit justified in a limiting reduction? And the answer he gives is that the values of the quantities evaluated at the limit, they should at least approximate the values of the quantities on the way to the limit. So for large but finite values of the limiting parameter m, we should get this approximate equality. So it's okay to have infinities when taking the limits. What matters for Butterfield is that as we approach the limit, we have this approximate equality. That's what matters. And what is physically real is the behavior on the way to the limit, not at the limit. Another way to understand Butterfield's principle is in terms of singular and regular limits. There is, of course, a discussion in the literature about this, about certain examples of limits, whether they are regular or singular, especially in quantum electrodynamics. So a regular limit is a limit in which the nature of the solution near the limit is similar and close to the solution at the limit, both in terms of its value and in terms of the structure, if you want. So this is a condition that has to be satisfied for a regular limit. And similarly, a singular limit is a limit in which the nature of the solution near the limit is fundamentally different from the nature of the solution at the limit. And you can understand fundamentally different as either in terms of the values of the quantity we're taking the limit of, or in terms of the different structure, and so on. So there is this nice example from Michael Berry, where you take the bite from an apple and you see half a maggot in the apple and you get disgust. And as you take the limit of the size of the maggot, the less maggot you find, the more disgusting it is. And this leads to the conclusion that if there is no maggot when you take a bite, this is the ultimate disgusting experience, which is apparently false conclusion because the limit is singular. The standard example from physics is, of course, phase transitions. Moreover, I think which is useful to keep in mind is that a regular limit can be justified in terms of a Taylor series. So if we denote the quantity of the general theory with G and the corresponding quantity of the narrower theory with S, and we have a limiting parameter delta, we should be able to expand the quantity in the broader theory in terms of a Taylor series and get these expressions like this. So if we take this as the orthodoxy, so to speak, of limiting reduction, we can identify three conditions for a physical theory to be reduction-wise justified. So a theory is justified in terms of reduction if it satisfies the following three conditions. Its quantities have to reduce to corresponding quantities of a narrower theory of the same domain by taking an appropriate upper or lower limit of a parameter, and this is a condition we call limits. The limiting operation has to be physically realistic and involve only regular limits, and this condition we call physicality. And the limiting parameter should not be arbitrarily introduced and should be able to be given a meaningful physical interpretation, and we will call this condition non-arbitrariness. Now let's go, okay, before we proceed to MOND, this is a standard example we can use. This is a reduction of the relativistic momentum to classical momentum. We have this relativistic expression here, and the idea is that we take the limit of this quantity, velocity over the speed of light. We take the lower limit, and we can recover the classical expression for momentum. Everything is smooth, physicality is satisfied, there is no arbitrarily introduced factor and so on, and we can also expand this in a Taylor series. So this is a standard canonical example of a limiting reduction. Now let's go to MOND and see what happens there. So as I said, this theory was introduced by Milgrom in 1983 to explain the flat rotation curves in terms of a modified gravity theory. The idea is that we can get the same phenomenology without the requirement of dark matter. And the underlying idea in MOND is that when accelerations are higher than the acceleration constant alpha 0, then we have standard Newtonian dynamics, and true acceleration, Mondian acceleration, is equal to Newtonian acceleration. However, once we go to the deep MOND limit, the deep MOND regime, where the acceleration is smaller than the acceleration constant, then gravitational acceleration takes a Mondian form, which is this one here, which is proportional to Newtonian gravity and the gravitational constant. Now, to ensure that there is a smooth transition between the two different regimes, when Milgrom first introduced his hypothesis, he did this in terms of what he called an effective phenomenological formula, which is now known as Milgrom's law, and it is formulated in terms of an interpolating function. So this is Milgrom's law, and you can see that there is an interpolating function, mu of he, where he or x is the ratio of acceleration to the acceleration constant. And of course, the constraint is that this interpolating function, when this factor here is larger than 1, so when we have accelerations higher than the acceleration constant, then this interpolation function becomes 1, and we have standard Newtonian dynamics. And when this factor is much less than 1, which means we're in a very low acceleration regime, which is what happens in the outskirts of galaxies, then this interpolation function becomes equal to he and gives us this relationship here for the deep MOND limit. This is the general idea. So this is Milgrom hypothesis, and up to today, the cornerstone of every subsequent attempt to implement Milgrom's hypothesis into a complete theory of modified gravity, including relativistic versions of modified gravity, is to actually reproduce Milgrom's law, right? There are several attempts. We will just take one example, which is AQUAL. But you have to keep in mind that what we say here applies equally to almost every attempt, because all attempts to implement Milgrom's hypothesis to complete theories of gravity, even in the relativistic versions, necessarily involve the introduction of an interpolating function. So if someone is interested in the details in the relativistic version, we have more details in the draft. You can let us know, we can share the draft at some point. So what's going on in AQUAL, which is an example of a complete theory of gravity implementing Milgrom's hypothesis? The idea is that we alter the gravitational action and we obtain a modified Poisson equation for a set of particles. This is a modified Poisson equation, and you can see that we have this interpolating function here. Now, this function has to satisfy some constraints as well to reproduce a desired phenomenology. And once we solve this equation, we get the equivalent of Milgrom's law up to a curve fit correction. So this is the reproduction of Milgrom's law. Now, these classical theories of gravity are, of course, toy theories for making predictions on the classical level at the galactic scales. And it should be noted that they are very successful in making very accurate predictions at the galactic scales. And they can also be used, and they are used as useful targets for the Wakefield limit of relativistic MOND theories. So relativistic extensions also require the introduction of an interpolating function to recover MOND and Newtonian gravity. The philosophy, the idea, the overall framework is pretty much the same. Things are a bit more complicated in the relativistic version because relativistic extensions of MOND not only have to reproduce Newtonian gravity in the low acceleration regime, they also have to reproduce MOND-like behavior in the ultra-weak limits. And they also have to be compatible with the predictions of GR in high velocities. So things are a bit more complicated, but what we say here applies equally well to those cases as well. Now, how about this interpolating function? As you might have guessed, the loose nature of the constraints on the function provides room for a variety of possible functions. And in the existing literature, there are indeed many different proposals about the exact form of the interpolating function. And interestingly, different interpolating functions seem to fit better in different kinds of data. One of the most commonly used functions is a so-called simple function, which is this one here. Recall that he stands for the fraction of g to the acceleration constant. You can easily see that this function becomes 1 when acceleration is high, and 0 and when the acceleration is low. But the key thing to keep here is that the aspiration is that extremely precise data from rotation curves and galactic dynamics in general in the future will allow us to pin down the precise form of the function, ruling out a large number of currently available candidates. This is important with respect to the condition of non-arbitrariness, because a plausible objection here is that this function is actually arbitrary. But the phenomenological arbitrariness of this function, of the form of the function, can be attributed to a lack of data, and therefore there's no arbitrariness here. Rather, it's just the fact that we don't have enough data to pin down the exact form. This is a possible argument to keep in mind. So how does limiting reduction work in AQUAL? Well, if we take the lower limit of the acceleration constant, which is equal to taking the upper limit of the limiting parameter he, for the Newtonian regime where acceleration is much higher than the acceleration constant, then our interpolating function in the Poisson equation becomes equal to 1. The modified Poisson equation reduces to the standard Poisson equation, so we get Newtonian gravity. Similarly, when we take the upper limits of the acceleration constant for the deep MOND regime, where the acceleration is much lower than the constant acceleration constant, our interpolating function becomes equal to he, and the modified Poisson equation, when solved, provides the desired MOND dynamics in which we have this new relationship for the gravitational acceleration. This is how we achieve the transition between the different regimes. Now, given what we've said so far, we argue that the reduction of MOND to Newtonian gravity actually satisfies the three conditions for a successful limiting reduction, at least as they are proposed in the existing literature. So the most straightforward condition is the condition of the limit, and we just saw that the quantity of Mondian acceleration reduces to Newtonian acceleration by taking the lower limit of the acceleration constant, or equivalently by taking the upper limit of the parameter x, which is this condition here, which is clearly satisfied. How about physicality? Remember that according to Butterfield's principle, we want the values for high, very large but finite values of the limiting parameter to approximate the values of the quantity at the limit. So for MOND, this translates to the requirement that as the theory goes to higher accelerations, then acceleration must smoothly become equal to the Newtonian acceleration, and vice versa. As the theory goes to lower acceleration, then we must shift away from Newtonian acceleration and gradually reproduce Milgrom's law. And once again, the introduction of the interpolating function in Milgrom's law ensures that this transition between the different regimes is smooth. And indeed, you can find various graphs in the literature showing how one goes from one regime to another in a very smooth way without any discontinuities. You can also go one step further and ask whether the limit is actually regular or singular. Now, if we make a qualitative assessment, it looks at prima facie the limit is singular, because what happens is that we have a deep MOND regime where we have MOND-like phenomenology and MOND-like gravity, and then once we reach the limit, the Newtonian limit, MOND behavior essentially disappears. So it seems that there is a structural difference, which can be taken as an indication of a singular limit. However, the introduction of the interpolating function is there to ensure that this is not the case, at least mathematically speaking, and that the behavior is smooth and doesn't involve any abrupt changes or any discontinuities. And in fact, the acceleration, when we introduce a certain any specific interpolation function, can actually be written as a Taylor expansion series. And this is what this slide says, basically. If you take, for example, the simple function, which is this one, and plug it in the equations, you get this expression for mondial acceleration, and this expression can actually be expanded as a Taylor series of G around alpha 0 and give you this Taylor series, ensuring that as we approach the Newtonian limit, higher order terms will vanish smoothly. Now, the condition of non-arbitrariness is the most tricky one. However, there is an important sense in which the limit is not arbitrary. And this is because the limiting parameter does indeed have a meaningful physical interpretation. This parameter is not derived out of nowhere. It is actually derived from various seemingly unrelated empirical scaling relationships in galactic dynamics, such as the baryonic Tully-Fisher relation and the mass discrepancy acceleration relation. These are empirical relationships between the mass, either the baryonic or the baryonic and non-baryonic mass of the galaxy, with the rotation speed or with the acceleration. And the common denominator the common factor in all this relationship is this particular parameter, which has a very well-defined value. And also, it is not introduced arbitrarily in the theory with the sole aim of recovering the limiting theory. As MOND scholars often argue, it plays a very similar role to the Planck constant in quantum mechanics and the speed of light in relativity in delimiting the different scales in which the theory can be applied. So it does indeed seem to have a physical interpretation and a well-defined role within the theory of modified Newtonian dynamics. So what I have just said is that basically MOND satisfies all three conditions for a successful limiting reduction. And at this point, I will hand over to Lorenzo, who will talk to you about the implications of accepting this position and the various subtle issues that arise with respect to interpolating function and modifying Newtonian dynamics in general. So I guess I can stop sharing my screen, and then Lorenzo, you can start sharing yours.
All right, you should be able to see the whole screen. Okay, so yeah, thanks, Antonis. Yeah, so I will just start by recapping briefly what we have just shown so far. So in a way, in a quite surprisingly way, we basically shown that MOND satisfies all the conditions for successful limiting reduction. So if we take limiting reduction as our standard account of reduction, this proves that MOND is reduction-wise justified in the sense that MOND bears the right kind of relation with the theory it's supposed to be reduced with. So we show that MOND satisfies the limiting condition because we get the right Newtonian acceleration from the Mondian acceleration by taking the limit. We've shown that this kind of limit makes physical sense, actually, despite the prima facie similarity of the limit. So the limiting operation has a regular limit, and the quantity can be expanded in a Taylor series. So this shows that the limit makes physical sense. And also we have shown that in the precise sense, which is introduced by Nichols, this limiting condition does not involve arbitrariness in the specific sense that the limiting parameter, the acceleration in MOND, is not arbitrarily introduced, and we can give a clear physical interpretation. which is also related to some kind of consilience in the sense that we get that acceleration also from other theories. So at least the limiting the parameter on which we take the limit on, it's not arbitrarily introduced. So we get basically to this quite surprising condition, quite surprising result, which is already quite an important result, we think, that it turns out that if we look at MOND through the lens of the standard account of limiting reduction, it turns out that MOND is a successful kind of, the reduction between MOND and Newtonian gravity is a successful kind of reduction. So MOND is reduction-wise justified. And in a way, as I said, this is quite surprising because there is this kind of consensus that there is that the interpolating function in MOND, the way that it is introduced in MOND, it's quite ad hoc. And even people in the MOND community acknowledge this, that there is some kind of pathological feature of the interpolating function. So the main concern, to put it a bit more carefully, is that the interpolating function within MOND is introduced basically exclusively to recover the Newtonian dynamics as we would expect. So the fact that it's introduced in this way makes it inherently arbitrary. And so despite the fact that MOND satisfies all the three standard conditions for limiting reduction, then we shouldn't take the limiting reduction of MOND to be justified. So there seems to be something missing here. And we think we can put the situation we are in a sort of, in the form of a dilemma. So the first one of the dilemma is basically biting the bullet and saying that basically, surprisingly, it turns out that MOND's introduction is actually justified. So MOND is reduction-wise justified. And these sort of worries should just be dispelled because MOND, the relation between MOND and Newtonian gravity is actually fitting turns out to be a successful case of reduction. Or we can go with the second or and say that actually satisfying limiting reductions three conditions as they are put in the standard account is not enough for successful reduction. So we think that the second one is much more plausible and sensible in a way, as we are going to argue. And basically this means that MOND is the case of MOND is pretty interesting because in a way MOND can be used to refine our understanding of a limiting reduction. And in a sense, I guess the other main goal of our talk is showing how, despite the fact that MOND satisfies the three conditions for limiting reduction, it turns out to be not a successful case of limiting reduction once we have a right understanding of what limiting reduction involves. So basically what we are going to do now, then in the rest of the talk, I'm going to propose two additional conditions for when a reduction is successful in the limiting case. And we show that MOND does not satisfy these two conditions yet, at least. And in a way, these two conditions are two ways to make more precise the non-arbitrariness condition. So basically our intuition, our argument is that MOND, although MOND doesn't violate the non-arbitrariness condition as set by Nichols in the original account, it's still arbitrary. The introduction of the interpolation function is still arbitrary in another sense, two other senses precisely. So the first point is the following. So this is the first proposal to refine the non-arbitrariness condition. So the idea is that we agree that there is some kind of arbitrariness involved in the introduction of the interpolation function. But the point is not just that any arbitrarily introduced interpolation is per se pathological. Actually, we should be more careful, and we should say that there are specific conditions that need to be the case for an arbitrarily introduced interpolation to be pathological. So one reason, which is the first of the two conditions, in this case, is the lack of a more fundamental theory which explains the interpolation function. So to be more precise, we think that there is actually an illuminating example, which is the case of Planck's law. So the idea is to use this kind of historical approach and to look at the introduction of Planck's law and draw a comparison with the case of MOND. And we think this is this gives us quite an interesting result. So the idea is that Planck's law for black body radiation is a well-known example of interpolation. So in a way, there is a similarity with MOND. The basic idea, which is a very textbook case of interpolation, is just that at that time, when Planck proposed the law, there was Wien's law and Rayleigh's laws, which were two laws to describe the behavior of black body radiation, which actually were successful and useful in a certain regime, but they didn't work in other regimes. So if you take one of the two laws and you move to a different regime, for example, in terms of the frequency of the black body radiation, then these laws stop working. And basically the proposal of Planck was to take these two functions and propose an additional function, interpolating them, which was designed to work in such a way that this new proposed law unifies the two proposals and gives us a unique function working at all frequencies. And the equation 16 here is just a standard definition for the standard case, the standard version of Planck's law. But the point here, the important thing to notice is that this interpolation was initially entirely based on intuition, and there was no solid theoretical justification besides the fact that the law works. And this is something which Planck himself actually acknowledges in his autobiography. So he's pointing out that so long as it had merely the standing of a law disclosed by lucky intuition, this law it shouldn't be expected to possess more than a formal significance. And that's why he was actually trying to find what he calls the true physical meaning of the law. He wasn't satisfied with this arbitrarily introduced law. But the interesting thing is that actually, if you take the Planck's law and if you confront it with the conditions for limiting reduction we have introduced, it turns out that actually Planck's law qualifies as well as a successful limiting reduction, just like the case for MOND. So the first point is that the condition for limit is justified because if we take Planck's law, then the law reduces to Wien's law in the high frequency limit. So you can see that on the standard diagram on the right here. And in the low frequency limit, the Planck's law reduces to Rayleigh-Jean's law. So basically, we just, starting from Planck's law, we recover the right laws at the right regimes. So the limiting condition is satisfied. Also, this law can just be expanded, the equation can just be expanded as a Taylor series. So the transition between Planck law and the other two laws is smooth, and there's no singular limit involved. And also there is no arbitrariness in the involving the quantity on which the limit is taken, because we are just taking a limit on the frequency. So this is definitely a sensible operation to make. So the takeaway here is that there is a strong similarity between the two cases. So in both cases, we have arbitrary and kind of ad hoc interpolations, and both cases satisfy the three conditions for a successful limiting reduction. But the interesting thing is that while MOND is not universally considered a good case, a successful case of limiting reduction, on the other hand, Planck's law is just considered a good case of reduction. There's no trouble involved in the introduction of Planck's law. And actually, it turns out that there are some major differences between the two cases, and they are not captured by the three conditions of standard limiting reduction. So the first difference is that Planck's interpolation, which is arbitrary, it does not involve an interpolating function whose physical meaning is unclear in a way. Here, the distinction with MOND is that in the case of MOND, we are introducing just a a kind of arbitrary function on top of our equations to recover Newtonian gravity. In the case of Planck law, we are just basically putting together expressions for the behavior of entropy at different scales, but there is nothing unclear there. But the main points here, the main differences, are the second and third point. So the first one is that although arbitrary, Planck's law was then justified within the context of quantum theory, especially through the principle of energy quantization. And also, and this makes the case for the non-arbitrariness of Planck's law even stronger, the law was later independently derived both by Einstein and by Bose, starting from the quantum theory of radiation and from quantum statistics. So it seems that although the two cases satisfy the three conditions for successful limiting reduction, there is another condition that we should pose, which is satisfied by Planck laws and is not satisfied by MOND, which is this idea that in the case of Planck's law, we have a fundamental underpinning, we have a fundamental theory which explains the interpolation, which we don't have in the case of MOND. So the take-home message of this example of studying this comparison is realizing that the interpolation is not problematic per se. So it's not just that it's not the case that any interpolation, which is kind of arbitrarily introduced, is problematic and makes reduction not justified. The point is that in the case of MOND, we don't have a fundamental theoretical framework that justifies the interpolation. So the quite interesting and quite surprising result, in a way, is that when we are looking at the limiting reduction and at the limit operation between relativistic and classical MOND and Newtonian gravitation, so when we look at this horizontal kind of relation, to understand if that horizontal operation, if that operation between MOND and Newtonian gravitation is justified, we actually have to look another level, a level below. So we have to find a way to justify the limit operation itself in terms of a more fundamental theory. So here's the point. The main point is that if we want to justify a limit between a theory and a theory which is narrower, we actually need to look at how the theory which is reduced is introduced and how it's embedded within another theory which is even more fundamental. And that makes a difference. And this is something which is actually also acknowledged by Mondians. In a way, they already acknowledge that we need to find a more fundamental theory to justify MOND. So this is basically the idea behind the introduction for this additional criterion for limiting reduction, which is not satisfied by MOND. So we call it downward theoretical grounding. And the idea is that the introduction of seemingly arbitrary limiting factors or interpolation functions to achieve a smooth transition between different regimes must be justified by solid theoretical grounds, which in this case is in terms of a more fundamental theory. So this is a criterion that's satisfied by the Planck's case, but it's not satisfied by the MOND case. And so this is already a first important point, but actually looking more closely at how the interpolation function is introduced in MOND, we realize that there is another sense in which the interpolation function is introduced in an arbitrary way. And we realize this basically by looking at how reduction works in the case of the relation between general relativity and Newtonian gravitation. So there is a strong dissimilarity here, just like in the previous example. So looking at the case of general relativity, the reduction between general relativity and Newtonian gravitation seems to be quite an uncontroversial case. And the idea is that the limit of Newtonian dynamics from GR just arises from the internal structure of GR, does not require any ad hoc modification. So in a way to picture this, we can say that you can imagine a scenario in which GR is introduced first, and then you can derive an effective, considerably simpler theory of gravity, which is Newtonian gravitation for low velocities, just starting from the framework of GR. So in a way, the mathematical structure of GR as the broader theory does not depend on the mathematical structure of the narrower theory, which is Newtonian gravity in this case. So the mathematics of GR is just independently introduced. And this is not what happens in the case of MOND. So this is the other sense in which the way the reduction between MOND and Newtonian gravity is introduced is arbitrary. The idea is that MOND's mathematical framework depends, at least at the present stage, inherently on the structure of the narrower theory. So in this case of Newtonian gravity. And this is problematic, we think. So as we said, MOND theories in the current form are essentially artificial patchworks. They are patches of two distinct mathematical frameworks. But most importantly, MOND is starting from the narrower theory to develop its theoretical framework. So the difference is that in the case of GR, GR provides a unified mathematical structure for different scales, and the narrower theory can be embedded into that. Whereas in the case of MOND, it's definitely less natural to imagine a scenario in which a classical or relativistic version of MOND pre-exists the narrower theory of Newtonian gravity, and to which the mathematical framework of Newtonian gravity can be naturally embedded. And the main reason, the main intuition behind this is that in the case of MOND, we are starting from Newtonian gravity to develop the more fundamental theory, in this case, MOND. So this is another sense in which, at least in the current form, MOND is not reduction-wise justified. The introduction of MOND is not a successful case of reduction. And so in the sense that MOND doesn't bear the right connections with the theories valid at other scales, but on the same domain. And we propose to add this additional criterion, which we call upward theoretical grounding, to capture this claim. So the idea is that the mathematical framework of the reducing theory, the narrower theory, should be naturally embedded in the mathematical framework of the reduced theory which is introduced, in this case MOND, and the latter should be able to account for phenomena at all relevant scales without resorting to the framework of the narrower theory in a sense. So basically what we have done here was to, as I said, introduce two additional criteria, which are downward and upward theoretical grounding. In a way, you can think about these two criteria as ways to specify the non-arbitrariness of the non-arbitrary nature of the introduction of the new theory in a way that goes beyond the specific and kind of coarse-grained non-arbitrariness, which was introduced by Nikos in the original account. So in a way, we made more precise in what are some more precise senses in which the new theory should not involve arbitrary factors like arbitrary interpolation functions. So just to wrap up quickly, and to just wrap up the main results of the paper. So we have shown that quite surprisingly, MOND satisfy the current standard accounts for limiting reduction, and so should be reduction-wise justified. But there is still this concern, which seems to be like a sound concern, that the introduction of the interpolation function in MOND is problematic. And we have shown that it's not just the introduction of an interpolation function, which is problematic. So it's not the interpolation in itself which is problematic. And we have shown this through the case of the Planck's law. Rather, the pathology, the issue with MOND should be found first in the absence of a more fundamental theory that can justify the interpolation. And secondly, in the fact that the theory lacks a unified mathematical framework which is independent of Newtonian gravity and from which we can embed and derive Newtonian gravity. So these are basically the main conclusions which are interesting for MOND specifically. But looking more broadly at the general literature on limiting reduction, actually the case of MOND is quite interesting because MOND provides a case study which shows how we need a more refined notion of limiting reduction, and we try to present that in the way I just introduced. So based on these 5 conditions rather than just the original 3. And that's it. Thanks.
Thank you both. If anybody has some questions on Zoom, feel free to raise your hand and I'll call on you to ask them. But otherwise, we can start with questions from the room.
Yeah, this is very interesting analysis and presentation. The new ideas you're introducing, basically you're saying that you need to have more physics when you make a generalization like this. So general relativity or special relativity, those are all fine because actually the new theory appeared in its final form, and its limit was the old Newtonian dynamics or Newtonian gravity. Everybody's happy. Suppose life had gone the other way. Suppose people were working with Newtonian dynamics for years and years, and then they started seeing small discrepancies, and then somebody came along and introduced a correction term of order v squared over c squared, just as an example. And then they said, here's a theory that fits observations better because I've got this particular discrepancy. This new term will take care of it. This is still not full Lorentz transformation. It's just a v squared over c squared correction. That would be kind of like MOND, maybe not quite, because the limit, I'm not sure how it will work, all of your requirements. But that I can imagine is a history where people will say, this is a hint of which direction we want to go or we need to go. But this is still not the final theory. And I think everybody will agree it's not the final theory until Einstein comes and puts the full Lorentz transformation. And then, it's also analytic. It's fantastic. And then you've got the whole story. Am I seeing this right or am I off the track?
Lorenzo, do you want to answer this? I think it's more relevant for you.
It's always hard. It's gonna
Yeah. Sorry, I couldn't demute myself. Yeah, I think you're definitely going to the right direction. So this is essentially the reasoning behind the first of our two additional constraints. So in a way, I mean, what we wanted to do was to propose a new constraint on successful reduction, which was supposed to capture this intuition which was missing from the original account, and which seems to be like a kind of crucial part of reduction. In a way, the reason why reduction is interesting also for physicists is that this gives us an interesting heuristic, and also it's an important heuristic and driving idea behind research, in the sense that, of course, like introducing like a small variation in the sense you proposed is a good starting point. But of course, we don't want to allow for any kind of arbitrary modification to work. I mean, we can just introduce arbitrarily whichever modification we want to accommodate the empirical data, but we don't want like a very, very scattered and disunified theory. So in a way, the condition to have like a more fundamental explanation is an important part of the heuristic behind the development of a more fundamental theory. So the idea is that we shouldn't stop there, and that's what Einstein did in a way. I mean, special relativity was already an important improvement on Newtonian physics in a way, but Einstein himself didn't think that was the last word, and that's why he was trying to develop general relativity as a more fundamental framework which explained the Lorentz transformations, for example. So
let me ask a quick follow-up here. Okay, so we'll stick to the special relativity example. So we've got the Lorentz transformation, which has got this new parameter, the Lorentz factor gamma. So the transformation doesn't depend only on beta, but there's a gamma correction, right? Which kicks in when you go to very large velocities close to c. Now, we love special relativity because gamma is a simple analytic function in terms of beta. We can say gamma squared is equal to 1 over 1 minus beta squared. Fantastic, we can do all the algebra, everything is great. Suppose nature had something like special relativity, but gamma is a function of beta, which is not easy to write in terms of simple functions. You needed an interpolating function of some sort. right? Let's just imagine this is how nature worked. Would you still consider it okay, or does it have to be analytic and easily manipulated rather than a function that somebody has to go and measure through experiments? How do you view that particular test example?
Yeah, I would say that that's an interesting case. I mean, we don't want to just say that you need like simple functions, or like that you need to eliminate away any kind of complex interpolation as a kind of like a priori condition. That would be like a too strong condition, would be quite unreasonable. I guess in that case, the idea is that you still want to justify, to find a foundation for the function you're introduced. Maybe in terms of like other principles or other laws, other theories. So in a way, you want that result to be like conciliant with our other results in other cases. And if the function turns out to be complex and not eliminable, it shouldn't be a problem as long as it like theoretically justified in that way. I don't know if Antonis wants to add something.
Yes, actually, basically what I'm thinking is that what we're trying to do here is to take science and see what is happening in current uncontroversial physical theories, which count as successful cases of elliptic reduction. And in particular, we take GR and the reduction to Newtonian gravity, and we say, okay, this is what happens here, and this is what everyone needs to be happy. And here is a case which is widely considered problematic, even by its own proponents. We should like remember that even within the MOND scholars, there is the requirement to remove the interpolating function. So we take for granted that this is not a successful case of limited reduction, and then we try to build up a framework as philosophers to see, okay, how can we distinguish between the two cases, right? Now, if I understand correctly, the question you're asking is, say that our theories in the future are more like MOND theories and involve interpolating functions which we do not clearly understand. Well, I guess in this case, we should sit down and think again whether we want an account of limiting reduction. How and where do we define the standards of successful cases of limiting reduction? And as Lorenzo said, this should probably will have to depend and look at other strategies. And we should also keep in mind that successful reduction is not the only requirement for a successful theory, right? So we didn't discuss other objections and other problems against MOND because they are irrelevant to our discussion of limiting reduction. But we should keep in mind that a successful recovery of a theory is not the only requirement to justify a theory in general, right? This is just one necessary but not sufficient condition, at least this is how we treat it.
Yeah, Peter.
I think the spirit of my question follows from Ganesh's, but in a quantum context. So in effective field theory, there are two ways of looking at the connection between low energy and high energy. One is from above, where you say we have these fields in high energy theory, and we integrate out those features that are no longer relevant at the low energy, and it gives us some terms, and that creates the effective field theory. That's of less interest to the working of theoretical physics in the context of the world we inhabit, where we often don't know some high energy theory, but there we use symmetry, we write down the terms, and some of those terms can have coefficients that are fixed by experiment, and we use that to be able to predict other things. The reason I bring this up is that in the low energy theory, where what the high energy physics is beyond the veil of our accessible theory at this time, we nonetheless can establish this, and we understand in some ways the relationship between high energy and low energy theory, whether from below or from above. Okay, so my question is, in the case of effective field theories, there's a natural scale. and or in each problem there's a natural scale, or the accessible scale of TeV and experiments at CERN or whatever it is. And I think you're trying to set a natural scale with, or MOND is trying to set a natural scale with some value of the A0. And my question is, is there a fundamental difference between the scale awareness of these relationship of the hierarchy of quantum field theories and the intrinsically unscaled relationship of general relativity or Newtonian or special relativity? They, in some sense, should apply at all scales. You can ask questions like, what happens at the limit, or does the limit, whereas if you have the Planck scale or some other scale, there are natural places where you understand your theory to break down. And so the idea that somehow general relativity is going to cover what happens at the singularity in a black hole is manifestly impossible, because there's quantum effects that will, of course, enter. So that my question is about whether the classical to classical problem is fundamentally different from the quantum to quantum relationship of effective field theories.
Yeah, this is a very interesting question. The short answer is I don't know. But I would say that there shouldn't be a fundamental difference. And basically the framework we are presenting here is about whether a broader theory recovers a more narrow theory. Whether there is a change in quantum or classical regimes is secondary, I think. And this is obvious in the case where we shift between relativistic regimes, the relativistic regime of GR and the classical regime of Newtonian gravity. Well, in the case of MOND, fundamentally, there seems to be a difference between the classical and the classical regime, which is what we are basically describing, right? But this doesn't really make any difference in how the theory reduces. Whether it is the fact that we have to shift from two classical regimes that calls for an interpolating function. This is an interesting question. I will have to think about this. But the cases of the effective field theories in quantum field theory, I think they are interesting case studies to see whether this framework we have just presented based on a single case study is something we can apply to other areas of physics, such as quantum field theory, and even whether it works well within the limit of other modified gravity theories, like classical modified theories of gravity, like f of t and so on. I don't know if Lorenzo wants to add anything to this.
Yeah, I guess just briefly, I just want to stress that what we are talking about is pairwise reduction between theories which are supposed to work at different scales, but in the same domain in a way. So that's like an important restriction in a way. So I guess in a sense, so in the case of MOND, the domain is just like the classical gravitational physics in a way. Maybe the example you made about the singularity and how generality breaks down there is a bit different in the sense that we expect that in the case of a singularity, we don't expect generativity to work there because we expect another kind of theory, which is like a quantum theory, for example, a quantum theory of gravity to explain what's happening there. So that's not the domain of generativity in a way. And on the other side, we are just focusing on the reduction between theories applied to the same domain. Then, of course, it's an open question if there's a way to make clear this distinction in a way.
Okay, David, then Laurent, and then I'll jump in myself.
Okay, so my question is, so you keep referring to MOND as a theory, but I would disagree with that. It's actually a framework for theories. So unless you fix mu, you actually don't have a theory. Only after you fix mu, you have a concrete theory of gravity, which describes this thing. Would you agree with that? Yeah, you seem so. So now, having an analogy is this, right? So there's this famous framework of nonlinear electrodynamics, where you basically start modifying the Maxwell equations. And so basically, what you require is that you take your Lagrangian to be function of the electromagnetic invariant f mu square, and you require that this approaches the Maxwell limit in the weak field regime. And then basically you can consider any modifications, any Lagrangians whatsoever. So I think all of these will satisfy similarly all three conditions. But then there is a distinguished theory, which is called Born-Infeld electrodynamics. And so that was postulated in the 30s by Born and Infeld. Basically, they were following the framework of going from Newtonian to special relativity. And so they wrote down the Lagrangian. It has very, very concrete form. It's like fixing your mu. So now my question is would this theory satisfy your additional criteria? So what is certainly not known is does it come from a more fundamental theory? It turns out that it has many unique properties. It was shown later that this theory has many unique properties, but it was also shown that, for example, it naturally appears in string theory, although not necessarily for just a description of point particles, but for description of charged brains and stuff like that. So would you say then that this theory, Born-Infeld electrodynamics, satisfies your additional criteria? Then.
Yeah, good question. Yeah, I think it's that's definitely going to depend on the details. I guess that my answer won't be very satisfying. I'm not sure if there's any like preliminary response I can give. I don't know if Antonis if you can see like already kind of a clear relation, but I think possibly yes, but it's going to be very highly dependent on the details.
I'm actually thinking the exact same thing, but maybe you know better whether it fits with our account. But the interesting thing here is that we are taking a case study, we're making a proposal, and actually this is work in progress. We started working on this very recently, and when discussing this project with Lorenzo, our thoughts about this is to actually see if we can apply this framework as it is to the reduction of GR from a possible theory of quantum gravity, right? And I guess one can find many different cases of limited reduction and apply them. Apparently, we didn't do this work yet, but it is surely a very interesting example we can look at. And maybe it turns out that one needs more conditions and we should like refine this even more, right?
Yeah, thanks for giving us another case study. In a way, this seems interesting.
Yeah, thank you for an nice talk. That's very interesting to me. I found the comparison with the way that Planck found the Planck function particularly illuminating. And I wanted to go back to a little bit to what you were saying as to, so if we push the parallel between the current situation and the situation with black body radiation before Planck's law, so we have two limits, right? The normal Newtonian regime and the MOND regime. So to some extent, the MOND regime is just saying that below a very low acceleration is constant. So this is kind of a theory by itself, you could argue, right? And then you're looking at the interpolation between the two. I would argue that this constant acceleration empirically is not particularly strong, right? I mean, there's a lot of people don't really believe in that situation. They just argue that there's more mass than we account for. But to some extent, the Planck situation was kind of the same, right? The Rayleigh Jeans limit was well justified theoretically by classical electromagnetism. But then there was the ultraviolet catastrophe, right? So the high energy regime was more like an empirical law. The Wien law was an empirical law that, if I understand correctly, was not theoretically justified either. And somehow this interpolation recovered both regimes and explains everything at once. Initially just as an interpolation, but then on quantum grounds, right? So I wonder, yeah, it's more a comment than a question, right? I find it interesting that we're here kind of in the same situation where the Newtonian part is very well justified theoretically as a limit of GR. The low energy part is, only empirically justified to some extent. And then we have this interpolation situation, right? And so it's more comment than a question. But I really, for me, the parallel with Planck was really illuminating.
Yeah, that's the hope in some way, right? That we have eventually a quantum theory that will explain, and then, the semi-classical limit, yeah.
Yeah, I think you're right. We are actually in a very similar situation. So in a way, I guess as philosophers thinking about how MOND works and how the research is working in that area, I guess we wanted both to show what's the problem with MOND exactly now, because we wanted to give an analysis of that. But in a way, showing this parallelism with the case of the Planck's law, we also wanted to, with these two additional criteria, to show how a way for Mondian people, showing what their theory should do in a way, what's missing basically from the theory to make MOND more like the case of Planck. So since the case of Planck is a universally considered now a case of successful reduction, the question was what's missing for MOND. So yeah, we think we actually agree. So I think we agree that the situation is kind of similar in a way, and that's actually the interesting thing to realize. So maybe MOND is not really doomed as like what many people think.
Lorenzo, can you please go back to slide 33? So if I can just add something, we can also understand our work as to trying to explain why MOND scholars are actually saying these things. So you can see that this is the first one is from a review of MOND, and the authors say that the concept of an interpolating function should fully disappear once a more profound parent theory of MOND is discovered. And here you have Milgrom, the father of MOND, if you wish, which says that MOND theory is proposed to date introduced by hand interpolation, blah, blah. Clearly, we need an underlying theory in which such interpolation emerges from the theory itself. So in a sense, we're trying to actually show and explain and understand why the interpolation function and the whole act of interpolation is considered wrong or pathological in the MOND case, whereas in Planck, it was later justified, right? Which is basically what you also said.
Okay, I'll take the last question then. So I have a question about your general methodology, and it's kind of a two-part. So the first one is, I think you're right that the reduction of GR is a great place to start building criteria, but I'm worried that it's so nice of a case that it kind of leads you to criteria that are too strong. And in particular, you get these criteria that this theory should tell you. I think it's demanding too much of the theory to explain things that future theory is supposed to give you. Having the upward and downward, I think is really nice when you do get it, like in the case of GR, but I worry that it's too strong. And I think this because you're starting with a case study that will give you sufficient conditions, but I don't think that it gives you necessary conditions. And so I think starting with the GR, you get sufficient conditions, but turning them into necessary ones that are then asked to provide justification for the theory itself, I think might be too far of a step. And my second part is, even in the case of GR, I wonder if it's right to think of reduction as a single kind of thing. I think Sam Fletcher has shown, you can think about weak field reduction. You can think about geometrical reduction of general relativity to Newton-Cartan theory. These give you different understandings of the relationship amongst the theories. And so another part of me is wondering if actually what you want is a plurality of kinds of criteria that you can have for different kinds of reduction. Like geometric reduction is talking about how the structures of the theories relate to the structures of some other theory, versus like the physical or weak field approximations are talking about getting back the empirical results. And these seem to work well together for the case of GR, but it doesn't seem to be necessary that they be unified in the same criteria of reduction list. Does that make sense?
Yeah. So this is definitely something we were discussing as well. So I guess the first goal of this kind of research was to try to look at good cases of reduction, compare them to MOND, and see which kinds of condition that are satisfied by those cases and are not by MOND. And so we have this like kind of heuristic proposal of these new conditions to specify more clearly what this non-arbitrariness can mean. But I guess like that being said, the thing that we need to work more on is to figure out if these conditions are necessary, sufficient, which one is really necessary, or maybe because yeah, as you say, I agree that it might be a too strong, especially the fifth one, maybe not the fourth one, but this one seems quite strong as it's formulated now. So it might be too strong. So it will be just a matter of time that we find the case which we want to say it's a successful reduction, but it's not. It doesn't satisfy exactly this condition. So we definitely need to think more about more case studies, and possibly these are not all necessary conditions in a way, especially the two conditions we added. And also the third one are not necessary in the same way the first and the second conditions seems to be kind of naturally necessary conditions a priori for successful reduction. Antonis, do you want to add anything?
I guess one can understand these 5 conditions as the ideal we were trying to reach for a successful case of limiting reduction. And a lot of what we said depends on the assumption we made at the beginning, that we take limiting reduction as a necessary condition for successful theory. But someone can challenge this, and I'm of course open to this as well. We might have a broader theory which has a different mathematical framework basically, and doesn't recover the more narrow theory, but nonetheless it should recover the phenomenology. And this would be a case of a good theory which is nonetheless outside the scope of limiting reduction. And of course this is possible, right? But insofar as we want to have broader theories that recover already essential effective successful theories, we somehow have to put some criteria or requirements of to distinguish between successful cases like GR and what are considered widely unsuccessful cases like MOND. And this is what we came up. Of course, yes, as this is like the general consensus, I think, from the Q&A, is that we have to see whether this applies to other cases as well, which is something that we haven't done yet.
Okay. Thank you both so much.
Thank you. It was a
Yeah,
pleasure.
Thanks a lot. Thanks a lot for having us and for the questions.